תודה רבה. כמו שאני נצלתי מראש שאני אביא את ההרצאה הזאת באנגלית. עם זה, it's the first time that I'm presenting this paper to a full-length seminar. I presented a short version of some preliminary results in Stony Brook, but I apologize in advance for any rawness of the material that I presented here today. So I think everyone here knows what Bayesian persuasion is, but let's go in slowly to say what exactly I'm trying to do here and why I think it's important. We know in general, I mean, if you just go back to the first week of our graduate courses of microeconomic theory, modeling a decision maker who chooses from a menu based on particular preferences, and we have very basic assumptions about preferences. We assume that the decision maker is going to choose the most preferred item from the menu. Now, in practice, we don't always see that. See that sometimes, I think that based on the expected value of the item given the distribution of the world, which one I think is preferred, but perhaps the choices don't match that exactly. Randomly, we're choosing. So, a natural hypothesis to consider in terms of why the passing from this menu would pass the report immediately by information. Meaning you receive some information about the state of the world that updates their belief regarding the best thing to choose, and therefore choose based on that information. Obviously, the best choice will depend on the respective posterior from the signal. Now, one particular case of where this information could come from is that the decision maker is being Bayesian persuaded. So there's some third party, we call it a sender, who is giving signals to the receiver in a way where they commit ex-ante to a particular distribution, and the sender has their own preferences regarding the outcomes of the actions that the decision maker is going to take, and on the basis of these preferences and what they expect the decision maker to do, they are generating these signals. So the question that we're going to address today is how do we test such a hypothesis? Namely that if we see a particular pattern of decision making from a set of menus, can we justify this pattern of decision making as arising from Bayesian persuasion from some unobserved set? Now, obviously the literature on Bayesian persuasion is huge. I think last I checked, there were several thousand citations on counting to JetScout. But actually, in terms of the empirical literature on it, it's actually fairly thin. There's very little that's been done to actually try to test this in practice. There's been some experimental work, but generally the experiments are pretty simple, and the payoffs from these experiments are sort of defined by the experimenters in advance.
Can you repeat, please, on the main question? Because what are the alternatives? One alternative is it's coming from signals. What is the other alternative?
I mean, there's various random utility models that could be.
Sorry?
Random utility models. There are various hypotheses one can consider. Later on in the talk, I'm going to compare in particular what are the differences and implications from the Bayesian persuasion hypothesis versus, say, the rational intention hypothesis, which there already is some work on in terms of how one would test that. And I'll show in particular that these have very different implications, despite prima facie having some similarities in terms of how we think of optimizing in those environments.
So I didn't get it correct, I think. So you can see a choice, you can see that the agent lay on the signal or something, you can see it.
I'll describe exactly what the analyst is going to see as I get to the model section, but roughly, yeah, there's going to be some observation of preferences and distribution of choices, but there's not going to be an observation of what the sender prefers, even if whether a sender exists. It's just a hypothetical object.
Okay. I ask a question. In Bayesian persuasion, there are incentives for the sender.
Right.
We ask, is there any sender? We ask also, are there any incentives for the sender?
Exactly, that's exactly the question I'm going to be asking. Can we find preferences for a sender such that we can justify this particular distribution?
We don't always assume that the sender is different.
Great, so I have something that eliminates that hypothesis as an assumption in the model, right? It's explicitly an assumption that I have in order to eliminate that hypothesis.
ניסויים, מה הם בודקים?
So in particular, they're like, you want to match the state of the world, and there are like two states, and we see whether or not they are actually sending the right signal in order to match the state of the world. It's something very basic.
אז הניסויים, כאשר הסטינג הוא שיש Bayesian persuasion.
Yeah, and they want to check whether they're doing where it's quite clear what the optimal distribution is. They're just checking to make sure that people are doing it or not. And so that's all that they're doing. But they're not doing something to actually test the hypothesis in the wild in a very general setting.
אבל הם לא בודקים את מה שאתה בודק. אתה
בודקים
אם יש סנדר, האם יכול להיות סנדר.
Right. Yeah, and then if there is a sender or not, these are things that you can check by linear programming algorithms, as I'll show later on in the paper. So these are the experimental work. There's a little bit other empirical work that tries to estimate signal design in some other papers. Ben Botter actually was a job market candidate who visited Israel a couple of years ago. I think he decided to go to MIT instead of coming here. And basically he was trying to estimate some model of signal design in healthcare markets. But what he did there wasn't even full Bayesian persuasion. He had a sort of parameterized set of partitions that you could consider, and it wasn't full. It was optimizing within this particular set and just estimating that. It wasn't particularly testing the hypothesis of Bayesian persuasion. Similarly, in this other paper, they're thinking about optimal monotone partitions of in a particular setting, and trying to test whether that's happening. It's not a general Bayesian persuasion framework. So there's very little that's actually been done in terms of empirical work to try to test Bayesian persuasion, and so as a result, this paper is what I think is essentially the first step towards how one would go about doing that.
אתה תיתן מוטיבציה לשאלה הזאת?
Oh yeah, so I skipped over that on the previous slide, maybe I shouldn't have. So if you think about like a newspaper that is, people often say like people are brainwashed by saying like Fox News in the US on the right or MSNBC on the left. So one could potentially test, like, do we see based on the sort of patterns of decision making that people make in response to the sort of things that are being broadcast there, whether this is actually consistent with them being persuaded by these particular news stations. Now, this is something I haven't actually explored. I'm actually looking for someone potentially on the empirical end who would potentially enable me to do that, but this is entirely theoretical work. But that's a motivation that a few people have mentioned to me that this might be interesting for. Okay, so what I do in this paper is use a revealed preference approach. Think about like Afriat in 1967, but there are a lot of papers since then that use similar approaches to what's called the state-dependent stochastic choice data set, where we see a distribution of actions from each menu conditional on the state. And then what I'm going to do is provide necessary and sufficient conditions for this pattern of decision-making to be consistent with the decision-maker being persuaded by an unobserved sender, where I don't restrict except very mildly to rule out this indifference. And I mentioned, I don't restrict the sender's preferences. I just want to make sure that these are consistent with Bayesian persuasion for some preferences. So there's going to be two key axioms that I'm going to present. One is no improving actions, which is, it's not a new axiom to me. This is a standard axiom in the literature. Basically says that conditional on the information that the decision maker has, their choice is optimal given their preferences. And the second is a new axiom, which I'm calling no act preserving posterior cycles. I'm going to explain what this means later on. And I also am not committed to this name. I'm not sure this is the right name for this, but I'll explain to what it is exactly. And as I mentioned before, these are all things that you can check using linear programming algorithms, so it's actually fairly easy computationally to check whether these conditions.
Why do you call it NIAS and not utility maximizing?
This is the name that was given in the literature, but it's basically an imputed. There's a sort of imputation of what the information is, and as a result, there's sort of inferred utility maximization, but we don't directly observe that they're maximizing utility. This might become a little bit clearer later on when I describe exactly how I define information there.
They may be able to increase the utility by several steps, and this assumption says no one action, or maybe something like this.
There's a way in particular, like the data set itself doesn't exactly define what the information is, and so there's a sort of step where we construct what it's without loss consider the information to be, and then based on that construction, expected utility is maximized.
המוטיבציה של הסנדר היא רלוונטית פה? יכול להיות למשל שהסנדר כל מה שהוא רוצה זה לעזור ל-decision maker או משהו כזה?
So that would be, I mean, then you just give full information. I mean, there could be other things that are potentially consistent with that, but weakly optimal, it would be best to give full information. Actually, under the assumptions I'm going to make that rule out indifference, overall preferences, overall distributions, it actually will always be optimal in the case that you mentioned, just to reveal full information. So, like, that would be the only thing that's optimal. But ex-ante, I don't rule that out.
משלים למודל.
Okay, so just a little bit more in terms of related literature. This isn't the first time that I've actually been working on these sorts of data sets in terms of real preference analysis. I'm mostly building on Kaplan and Dean and Denti, 2022. So Kaplan and Dean is general rational revealed preference checking for rationally intended preferences, where Denti extends that to posterior separable attention costs, where the cost of attention is sort of a function of the posterior belief, and so the total cost is the expected value of that function of the posterior belief. What I do in my paper with Kolomalik, who just finished doing a postdoc with me, is extending this to posterior mean separable costs. And this is also going to be relevant because I also have a section here on posterior mean-based Bayesian persuasion, as in Dvorak and Martini, so that comes up as well in terms of the connection there. Obviously, there's a connection to information design. Obviously, Alan Mashler, Kevin Zajenskow, in terms of the basic codification idea. Dvorak and Martini think about Bayesian persuasion over posterior means. And there's also this working paper by Lipnowski and Mathavet, which make a point that probably other people realize as well, but they make it explicit and give me a tool for the analysis I'm going to do to simplify the problem of checking the conditions for optimal Bayesian persuasion. So this is a relevant paper as well. Lastly, I want to mention a few other papers that have been trying to deal with some issue of axiomatizing preferences that are consistent with Bayesian persuasion. None of them do exactly what I'm doing. So these Jacobson papers are dealing with preferences over menus. So think about like Anscombe-Alman type of acts and then trying to say whether these are consistent with Bayesian persuasion. It's not a revealed preference type of characterization. Laura Duvall and Ronnie and a couple of research assistants have another working paper thinking about preferences that are not state dependent, that are consistent with receiving information, but they don't really have a general framework for adding the extra step of how that information is generated. And similarly for John Rebeck's paper in Jibo from last year, it's a similar thing. He has an application to a very simple case of Bayesian persuasion, but it's not a general way of thinking about Bayesian persuasion, it's just a very simple case.
אז נניח אצל יעקובסן זו אותה שאלה, האם ה-decision maker מופעל על ידי...
It's the same question, but it's like the difference between, say, Von Neumann and Morgenstern and or not even Von Neumann and Morgenstern, like what I'm doing is like Alfreat. What he's doing is more like the representation literature, like Von Neumann, Morgenstern, or Anscombe-Alman representation of preferences over actions or menus. So it's a different type of question. It's a closely related question, but it's not the same question. Okay, any more questions before I get into the model?
We are ready to the model.
Great. Okay, so the model is something very straightforward, and it's one that you're all familiar with. What I'm assuming is that both the decision maker and the analyst know the states of the world. There's some prior P naught. There's some grand set of actions, which I call X, from which finite menus are drawn. And there's going to be a utility function which maps from actions and states to real numbers. This is the utility function for the decision maker, who is in our hypothesis, functioning as the receiver. And so we can also define the indirect utility from a particular posterior to be the utility that the decision maker gets from optimizing their action from the menu.
For every menu, there's a different utility function?
No, it's the same utility function, but there's a different indirect utility function because when you're maximizing your utility from a menu, the optimal action at a given posterior could depend on what other options you have. Yeah?
So why is V a function of form A rather than form X?
Oh yeah, you're right. It should be from X. I changed that someplace, but didn't change it here. You're right. It should be a function from X.
Why is it indirect? Why do you call it indirect?
Because it's
Maximization,
yeah, it's from the maximization.
indirect utility.
Yeah, with indirect utility, like we see from standard
Consumer
choice.
theory,
Yeah,
yeah.
exactly. Okay. So this is basically the entire model, but what I want to talk about now is what the analyst sees from the choices of the decision maker. So there's a state-dependent stochastic choice function, sigma A, which maps from states of the world to conditional distributions over actions from that many. Using notation slightly, I've also used the same sigma A for the unconditional probability. And what I'm going to do, there's actually a decent amount of stuff going under the hood here, but what I'm going to do in terms of thinking about what is driving the choices of the decision maker is think about what's something that's been called in the literature revealed posteriors. Revealed posteriors are what we can think of as there being a single posterior at which the decision maker is choosing a particular action. The idea being that it's without loss to merge all the different posteriors at which the same action is being made in various environments. For instance, in information acquisition, merging several posteriors in which the same action is chosen would reduce the amount of information that's needed to generate that, and if information is costly, that's actually would be better for the decision maker. Similarly, in Bayesian persuasion, it's unnecessary to send more information than is needed to generate a particular distribution of actions. You can just merge all of those posteriors into a single one and just recommend a particular action there. We Cummings and Jenskow call this a recommendation strategy or recommendation signal for Bayesian persuasion. So without loss, we can merge all such signals into a single one. And then PA, capital A, would be the posterior, the single posterior at which this particular action is recommended. So it's solving by Bayes' rule, what would be the posterior conditional on all the distributions, all the posteriors at which the action would have been chosen based on Bayes' rule from the prior distribution.
האנליסט רואה את זה, מה הכוונה שהוא רואה את הפונקציה שהוא עושה סטטיסטיקה?
Yeah, so you can think of this distribution as coming up from repeated decisions of a similar nature over a large amount of time. He doesn't see a single realization of this. He sees many realizations of this. Now, this is a strong assumption. It's already been critiqued in the literature, but I will say that this is a standard assumption in the literature. It's something that I'll hope to get back to at the end of the talk to discuss a little bit if I have time. But this assumption is standard going back to Kaplan and Martin, if not earlier, and there was like maybe a dozen papers that already made this assumption. So
your ratio.
Yeah.
It seems to me that the denominator are both the same. What's the difference between the expression and the solid?
So no, this is hold on a second. Let me just double check this. So this is the posterior distribution. This is the probability of reaching that posterior distribution. Sorry, this is the probability of.
This This is the probability of A, which is.
Right, which is the probability of what?
It's actually the same, the sum.
Let me double check this.
Yes, it's the same. You claim it's 1, right?
There shouldn't be one, so there's something that I must have misread here.
Anyway, what is the meaning of this function?
The
What is
meaning-
the probability?
It's the posterior belief at which we impute that if this particular action is only occurring at a single posterior, this is the posterior belief it will have to be based on Bayes' rule from the pattern of decision making and the prior distribution of states.
This is the posterior on omega.
Yeah. Oh, I see. I see what the problem is. Okay, so this should be, I should have omega here, and I should drop the sum, and yeah. Okay, sorry about that.
So what it should be? Just
I should
No summation.
no summation and have the left side be.
You can write it
Yeah, I
down
know
if you
it.
like.
Again, I apologize. This is my first time presenting this, so
high technology.
yeah. So
With the light.
P A omega is equal to sigma A given omega P naught omega over sigma A.
This is the probability for state of the world omega.
Yes.
Ah, no, I understand.
You assume that sigma A of A is positive?
So that's assuming that's positive. Otherwise, I define it.
Okay.
to define
Otherwise,
it as
it means
not.
that
But
so the
if-
condition should be if it's also positive.
Well, that means it's in the support.
So,
So
yeah, okay,
yeah.
fine, yeah.
So honestly, I'm not really gonna reuse this, so I could have just defined it for A in the support, but in previous papers we defined it this way, so that's what I stuck with.
Just to be sure. So the analyst sees the capital A also.
Yes,
So he sees A and capital A,
yeah,
and from the revealed posteriors, this rule gives him the probability of omega.
yes. I mean, he sees the sigmas, so he can infer the probability of omega based on little a by Bayes' rule.
So why should he see little a? If he sees the sigma capital A, what
He
gives
sees
him?
that sigma capital gives him a conditional distribution of actions given the state. So he sees the distribution, essentially the joint distribution of actions and states.
Yes, and now he sees little a. It doesn't make any difference. It doesn't-
Right. I think you're leaning a little bit into that particular point, so maybe I need to be a little bit more precise. He sees the conditional distribution. I'm not assuming he's seeing a particular way. I'm assuming he's seeing a joint distribution.
Oh,
Okay, so the hypothesis we're interested in, which we are familiar with, is that the decision maker is being persuaded. So namely, there is a particular agent that is unobserved, namely a sender, who is trying to generate these signals to maximize their own expected utility. Sender's preferences are given by some little u, which also maps from actions and states to real numbers. So the receiver is going to maximize their utility given a particular posterior. So they'll choose a star that's going to maximize their expected utility, breaking ties in favor of the sender. And the sender, knowing this, is going to optimally choose the distribution of posteriors by some pi a. Now, going back to what Miguel said, we need to rule out trivial solutions, that the sender is just indifference between all possible distributions. I'm going to make an additional small assumption today, which is that the sender is always going to benefit from persuasion. I know how to extend it without that assumption, but I haven't actually formally written down yet, so I don't want to present it to you without that additional assumption. But we're going to assume that the sender always strictly benefits from persuasion for today's talk, which says that the utility the sender would get from just sending the prior is lower than they can get from some other distribution.
The posteriors pi a, so the.
That's the distribution over posteriors.
So what's p there?
P is a posterior,
A posterior.
and pi a is the distribution over posteriors for many a.
It's a posterior over omega.
Say that again?
Posterior over omega.
P is a posterior over omega.
And pi is a number of delta of omega.
Yes. Maybe I should have included that explicitly here. Okay. So I'm going to present the concatenation results of Hamilton and Jenskow in a way that's equivalent to the result, but maybe you haven't quite thought about it this way. So let me walk you through the way I'm presenting it here. So according to the main theorem of Hamilton-Jenskow, where we have calification, we can calify the utility function of the sender, and that gives them the value as well as the optimal posteriors for the sender's problem. Now, when we can calify, that means there's going to be a supporting hyperplane of the concalification of the sender's utility function that will indicate what is the optimal value that the sender can receive. As a result, there is some lambda a, such that for all a in the menu, such that a is in support of the signals generated, the utility at that posterior for the sender is equal to the values for that posterior on the hyperplane, whereas for all other posteriors, the utility would be weakly lower. This is equivalent to concalification. Questions about this?
Just a minute, let us digest.
חשבתי שזה פשוט שקול לזה שהפונקציה תיאורה.
Yeah, exactly. That's what
Concatenation?
Yeah, that's it. Okay. Just like, I'm not sure that people always think about it this way, so I want to make sure that, you know, this is the way we're thinking about it.
אני חושב שזה, אני מבין שהפונקציה תיאורה מזה, אבל מה זה קשור לקודיפיקציה? זו פונקציה תיאורה.
Well, U is the actually utility function, and we say that at the points of the support of the optimal distribution, we actually are tangent to that hyperplane. So the points of the support of the optimal distribution are actually on the concalification as well, but other points might not be, so they might be lower.
The sender solves the problem menu by menu.
Yes. So what's nice about this is that we now have a set of linear inequalities, and that's going to be very useful using the machinery that we're going to use in the talk.
So what is the difference between this and Afriat?
It's related to Afriat. So Afriat obviously is a different problem, but Afriat, I mean, I'm using the sort of machinery of Afriat here, but the point is that we can use this set of linear inequalities to rationalize this particular outcome via some preference that I'm going to construct.
Is this related to Alman Maschler?
Well, obviously, Alman Maschler is
One
Bayesian
direction of
persuasion,
Alman
so
It's one direction.
well, it's an if and only if. So yeah, I mean, it's concalification. That's what this is. So just like we're so used to thinking about actually constructing concalification that we might forget that actually what's underlying it or overlying it is a hyperplane. So.
Layer 1, it's the part that says that layer 1 can get listed up, right? Not the part that
Well, the part that they can defend it is that actually, well, I guess is that they're thinking of this.
I don't know, the part.
That's the added value.
Okay, so let's get into our axioms that will get us this particular representation. The first axiom is called no improving action switches, which states that for each menu and for each action in support of the SDSC function sigma A, the expected utility for the receiver or the decision maker, if they were to choose action A at the real posterior for A, is equal to their indirect utility. Namely, if this is indeed the posterior that they are seeing, then choosing A would indeed be optimal. This is a sort of a sanity check that ensures that what we've constructed is consistent with the rationality of the receiver. They're going to be maximizing their expected utility if indeed this is the information that they're getting.
So what is phi?
Indirect utility of the receiver at any way.
So you observe the posterior?
So I construct the posterior from sigma. I know what the prior is, I know what the conditional distribution of actions given each state is, so by Bayesian I can construct what the posterior is as if there's a single posterior at which this particular action is taken.
But why is there a single posterior? There will be multiple
There
posterior.
could be, but I'm treating it as an as-if characterization, and what I want is consistency with that. That's going to be an axiom that gives me
So this is an axiom not of the thing that you observe, but of something that you construct as part of
right,
the
you can
representation.
translate what you observe to this constructed thing, so indirectly this is an axiom on the thing that you observe.
כשאתה אומר as if אתה מתכוון למה שאמרת קודם, ה-merging posteriors.
Correct.
Does this limit you in some significant way? Assuming this axiom?
I mean, it's a pretty mild axiom. I think we would assume that if indeed they are choosing based on information, then they should be choosing optimally at the conditional distribution of this, but there could be other reasons that they wouldn't be choosing this way. For instance, you just have a random utility model wouldn't necessarily satisfy this axiom. Alright, so this axiom, again, has been used for a while. It's first introduced by Kaplan and Martin, and it's subsequently used by much of the literature. I should also include my own previous paper in here with my postdoc. There's like at least half a dozen, if not a dozen papers that use this axiom. Again, I'm saying it's just a sanity check to make sure that conditional on this choice coming from information, that indeed the choice that we're observing would be optimal conditional on that information. Now, the second axiom is really where the more subtle work needs to take place. So what I need to do first is describe something that's called a posterior cover by Lipnowski and Mathavet. So I think it's pretty easy to see in terms of the regions for a receiver where a particular action will be optimal, that these regions are going to form convex polytopes. So if I think about the simplex of posteriors for the receiver, I can subdivide the simplex into convex regions in which each particular respective action might be optimal. So this would be one particular subdivision of the simplex, which I'm going to call a posterior cover. It's going to be dividing the simplex into subsets in which each respective action is optimal. There could be obviously some actions that are never optimal, but I can divide it into convex regions in this way.
Each point is a state? Each point of the
Each point here is a posterior.
posterior.
So there's a convex region where A3 is optimal, A2, A4, etc. So what's important about the fact that these regions are convex is that we can look at the extreme points of these, and since it's a convex polytope, these are finite sets. So the outer points, these extreme points, are actually going to form a finite set of posteriors that essentially define each of the sets in the posterior cover. And we know that set is finite. In addition, I can represent any points in these sets by a convex combination of a finite number of points among the outer points of the posterior cover. And this gives me an equivalent payoff distribution where instead of a particular point, say in region A2, I could split them into the outer points and get something that would be equally good for both the sender and the receiver. So this gives me a finite set of points that I need to consider of additional or counterfactual distributions that potentially could be optimal for the sender. I only need to think about distributions over these points, and if I check that there's nothing better over these points, then I am convinced that indeed this is an optimal Bayesian persuasion.
You have just the action which is
optimal for the receiver, right?
Correct, but among the sender, if the sender's payoff is going to be affine in particular posterior, right? So if I split them within a particular set in the posterior cover, my payoff as the sender is going to remain the same. So, and in particular, if we maximize distributions over or affine functions, or if we maximize distributions that are piecewise affine, we can do that by screen points of these posterior covers. Okay, so let me roughly describe what the axiom is. So the axiom is that given the observed distribution of state-dependent stochastic choice functions and the implied distribution of posteriors, there's no alternative posteriors with support over these outer points of the posterior cover, such that Bayes' rule is preserved for each menu. The overall state-dependent probability of cross menus of each action as weighted by beta A remains the same, and we now place positive probability on the prior for some A. So we just need to think about alternative distributions over these outer points. We check whether there's an alternative distribution that essentially keeps the expected probability of choosing the action conditional on a given state the same across menus, and preserves Bayes' rule. If we can rearrange the probabilities in this way while also placing positive probability of the prior, that would falsify the hypothesis of no act preserving posterior cycles.
Jeffrey, you are going to explain each of these.
Yes, I'm going to give some examples of this.
כנראה פספסתי לגמרי. קרוס מניוס, למה קרוס מניוס? אני רואה, האנליסט רואה מה ה-decision maker עושה בכל מניו בנפרד.
Yeah, that's his data set. He sees the SKSC function for each menu.
אוקיי, סליחה.
So he thinks whether there's a way of rearranging what action is chosen in which menu stochastically in such a way that on average probabilities are kept the same, including the probability of an action being chosen conditional on a given state, while also now with a certain probability putting weight on the prior in some menu. So basically the idea with a lot of these sort of exercises that are in the style of Afriat is see if there's a way of switching around the choices so that now there's a choice where you're not supposed to have a choice. So here I've said you're supposed to never choose the prior as the sender as part of the hypothesis. If I can now at some point put positive probability on the prior for the sender, I put positive probability where I wasn't supposed to. If I can show that I'm preserving utility by doing so on average, while putting a choice where it's not supposed to be, then something has gone wrong with my hypothesis. So because basically I'm preserving Bayes' rule as well as the conditional probability of choosing each state, choosing each action conditional on the state, the expected utility for the sender should remain the same overall. The fact that I'm now putting positive probabilities somewhere where it's not supposed to be means that somehow I have lost utility when I'm not supposed to have lost utility. So something has gone wrong. But let's go into some more details on this. So the theorem is that a state-dependent stochastic choice function is consistent with non-trivial Bayesian persuasion, namely where we rule out that the sender is indifferent to all distributions, if and only if it satisfies no improving action switches and no act-preserving posterior cycles. Yeah.
So the appeal of the theorem is that it's difficult to check directly the dataset is consistent, but it is very easy to check the NAPBC axiom.
So they're both linear programming. What the analogy that's often given is, well, it's not even an analogy, it's directly mathematically correct, is thinking about NP versus co-NP. in computer science complexity classes. In terms of finding a solution to a linear programming problem, it's I think it's in NP. Whereas yeah, it's in NP because like once you have the certain potential solution, you can verify that solution in polynomial time. So if there is a solution, you can verify that in polynomial time. What I have here is saying, well, here's a way to violate the hypothesis that it's consistent with Bayesian persuasion. If I give you a distribution that violates NAPPC, I can also verify that in polynomial time. So I can both disprove or prove this hypothesis in polynomial time, given a candidate solution.
But in general,
In general, what?
so if you want to check if NAPPC satisfies or not, can
So-
you do it in a polynomial time?
So I think it's in NP because I think linear programming problems are computationally complex. But if you have a candidate solution, then you can say, well, it reduces to a linear programming problem. So whatever the computational complexity now,
Integer linear programming?
it's not an integer linear programming problem because it's the solutions don't have the integers here.
So why is it, it's not
It's a distinct one, why is it,
What?
why is it NP?
Um,
If you have one on Rn, then it's polynomial.
So I don't remember the exact computational classes, but the analogy in terms of the two directions of the hypothesis are NP versus co-NP. That I remember. So it could, if you can solve linear programming problems in general in polynomial time, then it's even better. But basically, it gives you a way of testing each direction using linear programming problems.
It's funny that you mentioned the best way to preserve. I never imagined it could be destroyed somehow. It's a rule of the.
Well, we have to construct this different function pi tilde a, and that's something that I have to construct that is also consistent from the same priors that is consistent with Bayes' rule.
So are you going to explain these points?
I'm going to give some graphs about this. I mean, I have some formal detail if you really want to look under the hood, but in terms of how one could construct such a distribution that violates this, I have a very simple example with a single menu that shows how you violate this even in a single menu.
I mean, I'm not guessing what you mean by preserving Bayes' rule.
So basically, if we look at the overall probability of each action being taken in menu A, we can calculate. Sorry, I should rephrase that. Pi tilde A gives a distribution over posteriors for menu A. What I need is that when I sum up all those posteriors according to the weighted average, that I get the same priors I had in pi A.
That falls in base.
Yes, that's what I'm saying. That's what the function pi tilde A has to be consistent with Bayes' rule from the same prior that pi A comes from. Okay, so let's give some intuition. First, let's go for the only if direction. So suppose that we know that we want to look at this distribution. We want to see. We want to say that if it's. Let's go over here. We want to say that if it's consistent with non-trivial Bayesian persuasion, then it must satisfy NIAS and NAPPC. Well, suppose that it violates NAPPC, then we have, but it's consistent with Bayesian persuasion. Well, we know if it's consistent with Bayesian persuasion, the prior was supposed to be suboptimal, so the optimal hyperplane lambda A dot P naught is supposed to be strictly above the indirect utility from the prior, according to the utility from menu A. However, we've reallocated the distribution of when the action is chosen across menus in a way that we preserve the overall probability of the particular action being chosen conditional on the state. So as a result, since all these things are linear, these payoffs, there must be some other posterior P such that now we are choosing P instead of what we were choosing before, and to compensate that, to keep this utility the same on average, we must have UB of P be greater than the optimal hyperplane that we were having before, which is a violation of the conditional of optimality for many UB. So as a result, sigma B must be suboptimal, and so we weren't optimizing our distribution for menu B. To give an example with a single menu of how this would look, suppose that I have a prior two states of 0.5 and I choose, and we know that these are the utilities for the sender for this menu conditional on the posterior, and the sender sends signals of 0.4 and 0.8. Now, obviously, this is not an optimal distribution. What would be a reallocation of posterior means? Sorry, not a posterior means. Reallocation of posteriors that would improve the payoff. Well, we can split 0.4 into a distribution that puts weight on this point and this point. So now we're putting positive probability on the prior. And since we weren't so supposed to be able to do that while preserving the expected posterior at which that act was chosen, we know that the original distribution was suboptimal. We shouldn't be able to get the same act chosen at the same expected posterior while putting positive probability on the prior. So this would be a violation of no act preserving posterior cycles.
So what are the blue lines?
The blue lines are the utilities of the sender conditional on the posterior from the optimal choice of the receiver.
What's the difference between the different blue lines? Different actions.
Different actions. Yeah.
Different actions.
Yeah. So the other direction is using the sort of standard tool of cyclical monotonicity that we.
But that's actually like a free up.
Yeah, it's coming with the same type of idea. I mean, I don't know if it's exactly cyclical monotonicity. Basically, a clever use of Farkash's lemma to construct a vector of scalars that basically are
So
like
essentially, this is why you needed the other accent.
Which one?
One of the longer one.
No act preserving posterior cycles. Yes. So that's why I'm calling it a cycle, but I'm not sure it's the right name because a cycle means that you're choosing the same points as you have had originally, but you're just moving them around. That's not exactly what I'm doing here. So it's like the same idea in terms of the construction as Afriata and all these other things, but since it's not exactly a cycle, I'm still shopping for names for this axiom. So basically, I use these linear inequalities and so it's something, if this axiom is satisfied, that means that we have basically a separating hyperplane from these inequalities that gives us a vector that keeps all these inequalities on one side, and we have this hyperplane that generates inequalities that rationalize this. And so these are the inequalities that give both the utilities and the optimal hyperplanes, and we can show that in instruction, these utilities rationalize the distribution of posteriors that the sender will be generating. Okay, so this is the basic model of optimal persuasion. What I'm going to do next is extend this to optimal persuasion over posterior means, and then hopefully discuss. I see I have 25 minutes, so I have to be judicious in how I use the remainder of my time here. Okay, so posterior mean-based Bayesian persuasion is a similar idea, but there need to be some modifications of the model in order to get this to work. So we're going to replace our focus on posteriors with a focus on posterior means, which I'm going to include without loss to be the interval 0, 1. There's a prior CDF F0 with support on that interval. I'm going to assume again without loss that includes the endpoints of that interval.
What would be posterior mean?
So I'm giving a sort of an interpretation of what the states are, so now they have a scalar value on the real line.
So the states are points on the real line.
Yes. So there's a prior Z0. We're going to need to include something about me preserving spread constraints in terms of what distributions are feasible. I'm going to expand on that shortly. We're going to again have the receiver's utility, instead of being functions from, here I have it as x, so here I corrected it, but before it's not. Here, utility instead of being from states to the real line, it's going to be, utility is a mapping from actions and posterior means to the real line. So we're treating all posterior means as being the same as long as they have equal value. The details of the distribution don't matter beyond that.
סליחה, התבלבלתי. הסטייט עצמם הם לא 0-1? הם לא קטע 0-1?
They are in that distribution, they are in that interval. But also, we're also going to define the payoffs as just depending on the posterior mean. So it's a stronger assumption about, implicit in this is a stronger assumption on the utility function that we treat any distribution of posteriors that has the same posterior mean as giving the same expected utility. Okay, so just to mention what I alluded to on the previous slide, we need to talk about what are feasible distributions of posterior means with respect to a particular prior distribution. So we are going to look at these distributions of posterior means. Posterior means need to be a mean preserving contraction of the prior, which means they need to satisfy this integral inequality. I've seen a bunch of different sources for references from this. A lot of people refer to Rothschild and Stiglitz 1970, but some people refer earlier to Strass in 1965, or even Little Hardy Little and Polia. So whatever you want to, whatever reference you want to use for this, you can derive it from there, but it's not a.
That goes back to 1940s.
1920s.
What?
Yeah. So yes. Whatever. I mean, I think like. There's sort of like a folk wisdom here that like we sort of worked out the details of this. I think this particular manifestation of this is from Rothschild and Stiglitz, but take that, sometimes other people cite other papers. So we're going to define the set of feasible CDFs as basically the set of distributions that satisfy this inequality for all points between 0 and 1.
And the Fs, the postulates do not have to have a finite support, right?
They do not, no. I mean, I'm going to be considering finite sets of actions for this exercise, so it's without loss that we will have finite support, but on principle, they don't need to. I probably could extend it. I mean, in my other paper with my postdoc, I actually did extend it to infinite sets of states and actions. It's a lot of technical headache, which for not very much gain in terms of intuition, so I didn't do it here. But technically, I probably could. Okay, so let's characterize optimal Bayesian persuasion for distributions over posterior means, where the center's payoff also only depends on posterior means. Then this CDF F sigma A is optimal if and only if there exists something that they call a price function PA, where this function PA is convex and affine at all intervals where the mean preserving contraction constraints is not binding. This price function lies weakly above the utility of the sender for all posterior means, and is actually coinciding with it at points in the support. Right, so what I'm going to need to do in order to extend my use of the idea that the sender has to benefit from persuasion in order to rule out non-trivial solutions is assume that the sender benefits from persuasion. Now, Dvorak and Martini don't have a result that characterizes this, so I needed a little bit of a lemma that says that a sender benefits from persuasion when you're thinking about persuasion over posterior means, if and only if one of two things holds. Either the price function is not affine, or the prior mean, UA of the prior mean lies strictly below the price function. So as long as one of those two holds, the sender strictly benefits from persuasion.
What do you mean a sender? So you don't have a sender, you have a theory of a sender.
I'm saying if under the hypothesis, if there is such a sender, the sender benefits from persuasion if this holds. obviously we need to test this hypothesis now, but this is an implication of the hypothesis.
So the alternative that the standard does not benefit from the persuasion means that he's indifferent.
Right. Well, or that his optimal, an optimal distribution of posterior means would be just standard fire. Okay, so I am able to extend my axiom from what I had regarding Bayesian persuasion over posteriors to Bayesian persuasion over posterior means by use of a similar axiom, which I have even longer dating now with no preserving posterior mean cycles. And I highlighted the differences in bold. So given the implied prior distributions of posterior means, there can't be alternative distributions and weights that are non-negative, such that the preserved Bayes rule, as well as the overall probability, as well as the expected posterior mean of a particular action across menus. And finally, we need to have a new additional condition. Now we both need that for some A, in order to violate this axiom, positive probability is placed at Z0, and the mean preserving contraction constraint is not binding for any point in the interior of the interval. So this last condition connects to what we saw on the previous slide regarding when the sender benefits from persuasion. Sender benefits from persuasion if the price function is not affine, or the prior lies strictly below the price function. The utility of the prior lies strictly below the price function. What's a way to make sure that we are putting something somewhere suboptimal? We either violate the mean preserving contraction constraint condition, where we have a non-affine price. That if we make everything have the mean preserving contraction constraints not bind, that means the price has to be affine over the entire interval. So if I break that with the alternative distribution, I know I'm doing something suboptimal. As well as putting something below the at the prior, this would violate the second condition. So I am basically making sure that I violate both possibilities of benefiting from persuasion at the same time by this alternative distribution GA. I'm both making sure that the price function is affine for GA, and I'm also putting positive probability at the prior. So as a result, I'm putting, as I said before, weight on posteriors where I shouldn't be, and that's going to violate the conditions for optimality for the hypothetical distributions. So as a result, I guess I didn't put the formal statement of the theorem, but if a state-dependent stochastic choice function satisfies both no improving action switches and no preserving posterior mean cycles, then the choice that we observe by the decision maker is consistent with posterior means-based Bayesian persuasion. Okay, so let's get into a little bit of discussion in the 15 minutes I have left. One big question that people in this area have asked me, and I think it's a very natural question, is comparing the implications of Bayesian persuasion with the implications of rational intention. In both cases, especially when you're dealing with posterior separable-based rational intention, is that the optimal distribution is defined by a concatenation problem. So,
in rational intention, the optimal quantification is a bit different.
Correct. I'm going to get to that exactly. But since they're both based on concatenation, the question is why maybe we would think that they would have similar implications. I'm going to show shortly that actually you can find cases that are consistent with rational intention but not Bayesian persuasion, and vice versa. So rational intention is that the decision maker is faced with a decision problem and starts with a prior distribution, can potentially learn more about the state by some sort of costly contemplation or costly information acquisition, and therefore gain information about the state relative to their prior. And then based on that, they choose from the menu. A common functional form of these rational inattention problems is something that's called posterior separable, which is a generalization of the sort of entropy-based rational inattention. So there's this function, often using the letter h, that is a function from posteriors to real numbers, such that the cost of attention is the expected value of this h function with respect to the distribution of the posteriors. So the natural question is, how do these things compare? Do we have, are we able to rule out one and not rule out the other? And the answer is going to be yes. The key difference is that in the case of rational inattention, it's both the decision maker is both the one who cares about the ultimate payoff, as well as the distribution of signals. So as a result, when we're trying to test whether a distribution of signals is optimal, we want to take into account the average decision maker payoff from the distribution of posteriors. In Bayesian persuasion, the sender doesn't really care about the decision maker's payoff. All they care about is the distribution of signals in order to maximize their own payoff, which is not part of the data set available to the analyst. So because there's these different things in terms of what they care about that will have different implications in terms of the set of data sets that are consistent with the respective hypotheses. So let's first show a case where no improving posterior cycles, which is the hypothesis, the axiom of Denti, does not imply no act preserving posterior cycles. So let's look at a case where no act preserving posterior cycles was violated, which was the graph I showed before, where we had these 4 different segments of lines, and we showed that that distribution is not rationalizable by Bayesian persuasion. But you can easily justify that by rational inattention by just saying outside of the points 0.4 to 0.8, it gets very costly to pay attention. So as a result, we can justify that by saying, why didn't he go all the way to 0.2 there? It's because it was just too costly to get that posterior. That attention is too difficult. So we can see, for instance, here would be a posterior separable cost function that would rationalize this. Again, the numbers are not particularly important. What matters is that you've got it very steep in the interval 0 to 0.4 and 0.8 to 0 to 1, so you don't want to go outside those intervals. So if we start with the indirect utility function and then combine that with the implicit cost from paying attention, this would be the net utility of the choice combined with the inattention, and then the lambda A, quite clearly shows that actually the points 0.4 and 0.8 are the optimal application. So we can rationalize the distribution that I had in the previous slides, where it violated no act preserving posterior cycles by some posterior separable cost of attention.
Where is lambda A in the picture here?
Why?
It says lambda A.
Yes, that's the optimal concatenation for a rationally inattentive decision
So
maker.
which curve is lambda A?
Lambda A is the dashed line.
45 degree?
Yeah.
Lambda A is a function of the 2 states, right?
Yes.
So here you have
Well, 2 states is a one-dimensional, similar to the one-dimensional line. So
y, it's a linear function, it's not a probability. Or it can be,
Yeah.
it's normalized to 1.
yeah. Okay, so that's one direction. We can also construct in the other direction something that satisfies any DEC, but not an ITC. Okay, so the idea, again, a lot of numbers on here, but the basic idea is that it could be that one particular set of actions is very bad for the sender as more information is as you get the mean preserving spreads, and one set of actions is very good for the sender. So in one case, the difference could be just that the sender wants the receiver to have information in one case, but not in the other. However, if you're rationally inattentive, if if you have if you have an increase in utility for more information from one pair of actions relative to the other, there's a comparative statics that if the benefit from information is greater in case A than in case B, then if you acquire information in case B, you're going to want to acquire information in case A. And as a result, that is not going to be consistent with rational inattention. So in particular here, I'm assuming that the benefit for information from menu A, where we have actions 1 and action 2, is going to be lower because the slope is lower than the benefit from information in case B, where we have A3 has a higher slope with respect to P than A1 does. However, we see the distribution that no information is acquired in menu B, but there is information acquired in menu 1, in menu A. So that would be inconsistent with rational intention, but that would be consistent with Bayesian persuasion, where quite simply the sender likes it when the receiver chooses based on more information in case B, because the like actions 3 and 4, sorry, the like actions 1 and 2 more than the like actions 3 and 4. So in particular, if we have these particular payoffs, we can rationalize these particular choices by saying actually information is bad in menu B because utility is increasing in P, so we want to put P as high as possible, conditional on action 3 being chosen. Whereas in menu A, where you have A1, payoff is decreasing in P, and therefore we want to put the action as low as possible. So as a result, we have different implications of the two theories. We can also think about other hypotheses that, going on to a different subject now. Some things that I haven't really discussed, but I think I need to extend the theory to. What I mentioned is that I'm only ruling out that the prior could be optimal, namely I'm assuming that the sender needs to benefit from persuasion. What I should also be thinking about is testing, maybe there are some cases where actually the sender strictly benefits from not sending information. So I could think about both testing the case where the sender benefits from information as well as cases where the sender strictly does not benefit from information, namely that if the prior is optimal, then necessarily we send the prior. We don't send any information. So as an if and only if characterization of what the decision is. Okay, so that's something I know how to test. I haven't written it up, but basically what you want to rule out is that they send alternative distributions that are not consistent with this hypothesis, namely they put posteriors on actions that are not the ones that are optimal at the prior. That's something I can easily do. Similarly, I might want to exclude other hypotheses where we want to say that this particular posterior not equal to the prior is also suboptimal. That's also something we can extend the theory to by similarly saying if we can reallocate posteriors in such a way that now in the alternative distribution pi tilde, we now put a positive weight at this particular posterior, we're going to violate the theory. So it's a similar idea. If we put something where it's not supposed to be, then we violate the theory. One thing that would also be interesting to potentially do, and I thought about it a bit, but there's some problems with it, is thinking about a reverse problem, where instead of knowing the receiver preferences, we actually know the sender preferences, and we want to ask, when is this consistent with the sender having to have their choices mediated by some third-party receiver who we have to persuade to act in a certain way. I'm stuck on this, I don't know how to solve this because the resulting inequalities of the optimization problem of the sender are quadratic in unknown parameters. And so I can't use the nice Arpash-Lemma techniques that I have available for what I'm presenting today, but if there's a way around this, it would be very interesting. Lastly, one additional natural avenue for extension, and this is something that people in this literature are concerned about, is the strong assumption needed on the data set in order to get the results. So we've assumed throughout that there is some state-dependent stochastic choice function, which the analyst has access to, and as a result of that has very detailed data on the choices of the decision maker, which is something that might not be so feasible to obtain in the data set. One direction in which people have been trying to weaken this is trying to look at data sets where we only know the overall distribution of actions. We don't see them as the conditional probabilities of these actions taken given the state. So there's some literature that tries to do that for human information rather than the theory of how that information is generated. So the Rebeck paper in GBO from last year, as well as this paper by Ortegal and Lanilat, have results on testing whether a distribution of choices that is not state dependent is consistent with a theory of choosing based on information. But by and large, these results don't combine them with theories of how that information is generated, and so I think this is still going to be an interesting direction for research, how to combine the results that characterize choice based on information with results for non-state dependent choice on how that information is generated. So yeah, that's all I have. I think we have a couple minutes for questions.
Your non-triviality assumption about the sender, it's something like is not indifferent between all
Right.
referrals action. Is that the actual condition, or is it just an intuitive way of expressing it?
It's the actual condition. I don't know what example.
For example, some action may be strictly dominated for the receiver. So they-
No, I'm assuming that he's strictly benefits from precision and we require strictly sub-opt.
אמרת שאתה יכול להיפטר מההנחה הזאת, נכון? או שפספסתי?
No, I can extend it, or what I can do is think about not just where the strictly benefit from all menus, but they choose non-trivial persuasion if and only if they strictly benefit from persuasion. So if they don't benefit from persuasion, then they send the prior, but it could be that there are other distributions that are also optimal. The hypothesis would say, in that case, they choose the prior, otherwise they send non-trivial persuasion. That's something that I can also test, but I didn't write it up for this topic.
In the case of the receiver, instead of quadratic function.
In the case where I know the sender preferences, but I don't know the receiver preferences, I would get a quadratic function in these unknown scales.
The theory that replaces linear programming is a semi-definite programming, right?
Right, but in terms of this like sort of Parka-Schlemmer characterization, it becomes much uglier. So
The issue is that
yeah. So with a convex cone, you get a very nice. You know exactly where you need to compare to. With a non-convex cone, when it's not a convex cone, you don't know where the hyperplane is supposed to go, and it becomes much uglier. There's this. I was looking in a book on revealed preference. There's this theorem called the positive Stellensatz, which is related to the middle Stellensatz that characterizes what if the
This
Jekyll
is really quite complex.
Yeah.
Definitely is specialized for.
Right, but from what I was seeing in the literature, I didn't see clean if and only if results. If you know something, I'd love to see it, but I looked and I couldn't find it.
איזה סוג של ניסוי היית עושה בשביל הג'דר הזה?
I mean, you could run an experiment. I mean, I talked to Martin about this. He said he didn't see so much value in running experiments on this because like in general, people don't behave according to these theories in general in the lab. And yet another experiment on the theory like this, he thought it had limited value. He thought it would be more interesting to look at a particular data set, like for instance, how people behave in reaction to news. And there are people in Israel who work on that, so I'm trying to discuss with them how to proceed maybe in terms of an empirical approach.
What is there to test empirically?
I mean, you can look at, for instance, voting patterns or at least self-declared voting patterns in reaction to,
Also whether the action was satisfied.
yeah.
But you have to somehow know what are the beliefs.
No, you don't need to know that. You need to actually, as an analyst, know what that true state is, which is also a complicated. It's like somehow the decision makers don't know what the true state is, but you as the analyst, the competition, need to somehow know that. That's, I think, the difficulty. Okay.